Hello, once again, historical geology enthusiasts. We are here today to continue our discussion about plate tectonics. So when we looked at our globe, what we said is that there are 7 major plates and 12 minor plates. And we've identified the terms convergent and divergent. So when we look at our globe, we know that it is a dynamic system, but it's either gaining mass or losing mass, because what's happening is that the divergent plate boundaries are balancing the movement and subduction of those convergent plate boundaries. Plate tectonics and each of these plates have variable rates and even variable rates within the plates themselves. We can think of Iceland as an example. So the divergent plate boundary that's cutting Iceland in half is moving at about 1 inch per year or 13 miles per million years. So we can think back to our very first discussion about rates and how we can think about 1 inch per year being really slow, but when we total that up to a million years, that is a pretty big distance. So 13 miles per million years. So it can have a huge impact on the planet. What we're going to do today is we're going to talk about the history of plate tectonics and the origins of where this discussion originated. But first, as we look at the map that's on the screen, I'm showing you an elevation map of the surface topography, the surface landscape. And we can look towards Greenland over there in the northern hemisphere, and then we can focus on Antarctica on the bottom of the globe. And you'll notice that those elevations are in warm colors, which indicates higher elevations. So the question to you, my viewers at home, is what's causing there to be upper elevations in Greenland and Antarctica? And hopefully you're tying that into climate. So the polar regions are colder, and so what we're looking at is ice sheets. So those are the 2 major and last remaining ice sheets on our planet. And they both, although they have variability, they range from anywhere from about 2.5 miles thick to about 3 miles thick. Moving along, we can focus then on the North American continent and the elevation that we see on the western seaboard. And we would know that locally as the Rocky Mountains. But when we consider the mountain range as a totality, we consider it the North American Cordilleran, so spanning all the way from Alaska through Canada, down our western coast and into Central America. So the whole system that formed at similar times is called the North American Cordilleran. When we move south, we can look towards the Andes Mountains. And what's interesting, when we look at this elevation map, then you can see the Himalayan mountain range, and it's the only mountain range on our planet that runs from east to west. And so that's between the Indian continent and the Eurasian plate. And so you might remember from our last discussion that that is a continent to continent convergent plate boundary that's forming those Himalayas. And then when we focus our attention on the oceans, we can see something that's called the mid-ocean ridge. Write that down. So the MOR is the acronym for the mid-ocean ridge, and that essentially is a divergent plate boundary that spans the globe. And so you can look at the central features of the Atlantic Ocean, and you can see that mountain chain, and that is a divergent plate boundary in the center of the ocean, and it circles the globe. So when you're out playing trivia somewhere and they ask you what's the longest mountain chain on the planet, you're going to say it's the mid-ocean ridge. You're welcome for that. I hope you win some hot wings or something. So we started this discussion because we're not the first people to ask this question about the location of mountain ranges on the planet. So this story goes back to about 1700s. And the initial questions that scientists were asking included, why were some mountains taller than others? Why are mountains concentrated on the edges of continents? How did the rocks get folded into within the mountains? So they were looking at the physical characteristics of the mountain ranges and asking these questions simply based on observation, mostly because that's the only tools that they had in the 1700s. Why are some mountains taller than others? We can make comparisons between the Rocky Mountains versus the Appalachian Mountains. So the peaks in the Rocky Mountains can be upwards of 14,000 feet, whereas when we look at the Appalachian Mountains, at best, they're around 6,000 feet. So why are the Appalachians smaller in height than the ones that we find at modern day on the West Coast? Why are mountains concentrated on the edges of continents? So again, we can make a comparison between our western seaboard and our eastern seaboard, and we see topography on both of those. And then how did the rocks get folded within the mountains? So even if we take a walk up Lavender Mountain, we can see that the rocks are bent. And what we learned last week when we talked about stratigraphy and the principles of Nicholas Steno, one of the foundational principles was that the rocks are deposited, and they're deposited originally horizontal, so they're flat. So something must happen in the environment to create them to bend or fold. So when we look at scientific literature in the 1700s, this is some of those initial discussions. And there were two main players that were formulating these different talks. And we can make comparisons between a West Coast scientist and an East Coast scientist. So it's making comparisons between Hall versus Dana. And this was a discussion that was written in 1850. So what's interesting to think about is that this was really before scientific collaboration. So Thomas Edison doesn't open his laboratory in Menlo Park, New Jersey until about 1960, 1970. And what's interesting about that is that Thomas Edison in his Menlo Park lab was the very first collaborative lab, an interdisciplinary lab. So he was trying to make all these inventions of his work, and so he's bringing in different people to try to answer those questions. So he had biologists and chemists and physicists on staff working on the same type of problem. So before that, that scientific network idea became, people were working independently. And of course, it's very hard still in 1850 to communicate from the East Coast to the West Coast. So the development of very different ideas on how mountain building progressed came out of this, because they weren't communicating or sharing ideas. So Hall's hypothesis was looking at how sediment on the surface could influence the basement bedrock. So what Hall is suggesting is that you have erosion, and erosion is going to break down that sediment. And although it's going to cause the underbody to warp and bend and fold, what's going to happen is you're going to get more and more sediment piled up on the surface. So it is that sediment that is causing the mountains, essentially. So the basement rock is giving weight, but you're getting sediment piled on the surface, and that's what's causing the topography change, which is different than what Dana was suggesting. So Dana's suggesting that the less dense sediments will not depress the more dense basement rock. And so instead you end up with, you must have to have some type of compressional forces to cause the uplift. So he's suggesting that it's not just simply sediment deposited on the surface, something else must be happening. And in 1850, that something else, the mechanism, is not being addressed, but he's just suggesting that there must be some type of larger influence. So honestly, Dana was more along the lines of the theory of plate tectonics than was Hall, but they were still trying to answer similar questions. So Dana is calling this vertical uplift. And so he's suggesting that there is probably some type of squeezing and there's some type of upward uplift that must be happening. So as we move forward, those discussions are going on in 1850. They're writing their scientific documents. There's another fellow that's going to come on the scene that's named Alfred Wegner. So Alfred Wegner is German, and he lived from 1880 to 1930. And here's a picture of Alfred Wegner. Like many of the scientists living in the earlier 1900s, Alfred Wegner was not classically trained as a geologist. He was classically trained as a meteorologist, remembering that the textbook of the Principles of Geology wasn't written until 1865, so just before Alfred Wegner was born. So geology was a relatively new science, but he was a naturalist and he was interested in understanding meteorology. So he does it for a while. Alfred Wegner is independently wealthy, so he's able to travel the globe. And he's traveling the globe for leisure, but he's also interested in meteorology because that's what he's classically trained to do. And so he's asking some questions about the natural environment around him, and he's writing these things down as he travels. Alfred Wegner is the first person to coin the term Pangea. So Pangea is what we call a supercontinent. So when all the plates come together, that forms a Pangea. And when we talk about Pangea, we separate that into two parts. So the first part is going to be Laurasia, and the second part is going to be Gondwanaland. So Laurasia is going to be the northernmost continents that form above the equator, and Gondwanalands are the continents that are below the equator. So Laurasia is going to be North America and Eurasia, and then Gondwanaland are the continents of the others. So South America and Africa and Australia and Antarctica, and we'll throw into the mix India. So if you look at the picture, the diagram that's on the screen, you'll notice that India is part of Gondwanaland. So eventually India will move and collide with Eurasia, crossing the equator. Antarctica is the only continent that never moves above the equator. So Antarctica is the only continent that is always going to remain in the southern hemisphere. So as Alfred Wegner is investigating and traveling, one of the things that he first noticed is something that's very basic. So he's developing these ideas for Pangea and this idea of a supercontinent, and these are the lines of evidence that he begins to use. So the first one is some continents clearly fit together. So he looks at the South American continent and Africa, and he says, if this were a puzzle, it sure looks like these continents were up against one another. And then the other example that he uses is looking at Africa and the Arabian Peninsula. So you can go ahead and locate that on the modern day plate tectonic map over here on the right. So the African plate is highlighted in that teal color, and then the Arabian Peninsula is highlighted in that orange color. And what you'll notice is that there's a divergent plate boundary that's separating the African plate from the Arabian plate. Alfred Wegner didn't know that, but what he did know is that looking at an image, a map of the African continent, he's saying, it sure looks like the Arabian Peninsula was once part of Africa, but something happened to cause the splitting, and so the formation of the Red Sea and the Gulf of Aden. Tying it back into the principles of Nicholas Steno that originated in the 1600s that were published by Charles Lyell in 1865, we can talk about that idea of lateral continuity, right? So even though you have the parting of the Red Sea, what you see on that Arabian Peninsula should look exactly like and mirror what you find on the western side, on the African side. And sure enough, Alfred Wegner was able to identify that continuity. So these are questions that he began to ask, well, what had happened to cause them to separate? And the South American continent moving away from Africa is a much bigger area of movement, right? You have an entire ocean that separates the two. And here you have a much smaller localized example. So he's also thinking in terms of rate and time of how these processes have happened. So continents fit together is the first line of evidence. The second line of evidence has to do with index fossils. And had we been in class, I'd bring in examples of these. An index fossil, and go ahead and write this down because fossils are going to become very important in terms of historical geology as we move forward. So an index fossil is one that is geographically widespread. It is unique and easily identifiable, and it lives between a constrained period of time. So it's geographically widespread, it is easily and uniquely identified, and it lives during a short geologic time period. So that's considered to be an index fossil. And index fossils are important because it helps you to identify stratigraphy. A local example of an index fossil is called a trilobite, and we'll take a look at trilobites when we start to identify invertebrates. But a trilobite is a trilobite is a trilobite. There's nothing in the fossil record that looks like a trilobite, and that's kind of the idea. And these are three different index fossils that Alfred Wegner used. So the first one is Glossaria flora, which is a type of Pennsylvanian fern. So it's a fern that's very unique. And what Alfred Wegner was trying to do was to look to find, as he's traveling, these index fossils and where they're located. So what we'll notice from this diagram is that the Glossaria flora is in green. Fake news, it's in orange. And so we can find it on the southern tip of South Africa, on South America. You can find it on the southern tip of India, on Antarctica, and also on Australia. So you find it on all the different continents. And so that makes Alfred Wegner curious because remember, he's a meteorologist. So he's like, how in the world can you have this same type of index fossil that is a fern on all these different continents that at modern day have such different climates? So how does this show up in the fossil record in Antarctica but also show up in Africa? And then remember too that India is now part of the northern hemisphere. So at modern day, India is part of the northern hemisphere. So how can you find this in the fossil record on all these different continents at the same period of time? So he becomes curious as to that. The next is the idea of the mosasaur. So the mosasaur is in the lower left-hand corner, and mosasaur was kind of like a modern day alligator. So they were super sensitive to saline water, first of all. So when we look for the signatures of the mosasaur, we find the mosasaur on the southern tip of South America, and we find it on the African continent. And so Alfred Wegner, remember, first identified, wow, it looks like those continents were once together. But now when he's looking at the mosasaur, he's asking the question, how in the world could this freshwater dwelling reptile move from the South American continent to the African continent? Like, how could it get from point A to point B without crossing that ocean? So this is making him think about, well, maybe South America and Africa was once together, because otherwise it doesn't make sense logically how this reptile could physically move and survive from one location to the other with crossing the ocean. And the next is a lysosaur, and the lysosaur is up here in the right-hand corner. Lysosaur is one of my very favorite fossils that we find in the early Triassic record. Lysosaur is kind of built like a hippo. It's still reptilian, but it's kind of built like a hippo, where it is not built to swim. Like, it's not built to swim great distances. And here, when we look at the lysosaur in the fossil record, you find it on Africa, you find it on India, and you even find it in Antarctica. So he's asking the question, A, about climate, but B, also about, like, how could this lysosaur move from these different locations unless the continents were all up close together. So continents fit together. He's looking at the index record fossil for these various things. And the next thing that he's asking about is going to be about Paleozoic glacial deposits. Okay, so again, remembering that Alfred Wegner is a meteorologist, so he's interested in how climate has changed. And remember that during this time of 1880 to 1930, we're undergoing the Huttonian Revolution. Remember, so like there's been a shift in thinking of the Earth is only 6,000 years old to thinking like the Earth is much older than 6,000 years old without being able to absolutely assign a date to it, but suggesting that the Earth is millions of years old instead of thousands of years old. And so thinking in terms of how that climate has changed and fluctuated over time becomes an important concept as Alfred Wegner is going through the mechanisms of understanding these plates and how they may have moved over time. So Alfred Wegner hooks up with another geologist, and they begin to identify where they think past glacials were. And so what you understand is that glaciers are dynamic systems. They move from high gradient to low gradient. And as they do that, you can have, like we do now, like 2 miles worth of glacial ice in a location. And that's a lot of weight. That's tonnage of weight on the bedrock. And so as it moves, it's scouring that basement rock underneath it. And so as it's moving, it leaves these things that are called glacial striations. And that's what you're seeing on the picture on the right. So the cool thing is that not only do you have an understanding that there was a glacier in that past location, but you can also trace how that glacier moved in the landscape. So looking at the map on the left, Antarctica in the Paleozoic, so Paleozoic 570 million years to 248 million years. Paleozoic, Antarctica was glaciated. That was the center of the ice sheet. And then you could tell by the striations the direction of which that glacier was moving. And so, there's like the question, like at modern, right, present is the key to the past is the key to the present. At modern day, first of all, there's not glaciers in South America, Africa, India, or Australia. B, how could the Antarctica ice sheet act as a center and spread onto the edges of Australia, South America, Africa, and India if they weren't close together? Like if they weren't unified as a supercontinent, how could that happen? So this was a very convincing argument for Alfred Wegner. Up on the canvas under the week for this module, I'm also going to put up a Google Earth image where this picture was taken. So this picture was taken in a place that's called Kelly's Island. And Kelly's Island is a small limestone island that is in Lake Erie. So I can pull out the map of Michigan, right? Lake Erie is over here on the eastern part of the state. And so there's these tiny limestone islands that you can visit. Kelly's Island is one of those. And what you'll remember us talking about the very first day of class is that this area of Michigan was completely glaciated 14,000 years ago, which was called the last glacial maximum. So you're imagining 2 miles worth of ice standing on top of Michigan, Ohio, and regions to the north. So as that glacier came down and moved into Michigan and Ohio, that's where you see these glacial groove deposits exposed at the Earth's surface. So they're spectacular and give us a clue as to what had happened in the past. So Alfred Wegner, then he looked for these types of glacial striations on these different continents and in fact found them and then was able to assign a direction to them. So by about 1910, Alfred Wegner presented the idea of continental drift based on this evidence. So he says to the scientific community, and remember, he's a meteorologist, he's a naturalist, he's taken serious, unlike Nicholas Steno, right, or Jim Hutton. So he was taken to be serious, and he presented the idea that the continents were once completely together, and he called this his ideas of continental drift. And at one time, the continents had drifted together to form a supercontinent. And when he did this, he had a lot of skeptics come after him. So the haters came out. And the haters were saying, Al, ha, 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 like, this is a really big idea. You're saying that these massive continents move over time. How? And that's the big flaw. And that was a big flaw that Dana and Hall also had, was that they suggested ideas of mountain building, but they didn't provide what? A mechanism. So they didn't provide a suggestion as to how they were moving. So he gives his line of evidence that reasons why he thinks the plates are together, but the motion of getting them together is what he did not present. And so there's a lot of skepticism towards his ideas of continental drift. And so from 1910 to his death in 1930, Alfred Wegner is trying to solve that question. And so he makes some suggestions about, well, maybe it had to do with like gravitational pull of the moon on the land surface, and maybe the tides had an influence on the position of where these continents were. And he starts to think about magnetism, but he doesn't really come up with an idea that people hold on to. And remember, for something to become a theory, it has to be testable and repeatable. That's a big part, right? So you make a scientific observation, you test it, you ask a question, you test it, repeat it, and then your colleagues can also test it and repeat it. And so he dies without knowing that his ideas of continental drift are going to become really important in the future, unfortunately. So what I can tell you is that the ideas of continental drift are not going to be revitalized until the 1960s. So my question for you is, why? So Alfred Wegner introduces the idea of continental drift in 1910. He studies it with good intention until his death in 1930. And people don't revisit this idea until 1960. So there's like a lag. And there's a lag, honestly, in the entirety of the scientific community. So it's not just geologists who have stopped revisiting this question. Everybody stops revisiting this question, and others. And that's because between 1930 and 1960, science was driven towards what? Towards war. So coming out of World War I, moving into World War II, and then rebuilding after the war. So unless science was being used for the purpose of war or rebuilding after war, there's kind of a lull in the data set. So people aren't asking questions just for the purpose of asking questions about science. So by 1960s, time on the planet begins to settle down a little bit, and science can resume itself. One of the big players in answering the question and the revival of this idea of continental drift is going to be tied to a fellow by the name of Henry Hess. And so Henry Hess is out of Princeton University, and he is a professor, a visiting professor. And Henry Hess is a geophysicist, but he was also a captain in the Navy. And one of his major roles and contributions to World War II was distributing where and when and what depth submersibles were going. So submarines, he was in charge of the submarine arsenal. And so Henry Hess was privy to what was being explored on the bottom of the ocean floor. And he worked, so when he, so there was some like underwater mapping that was happening during World War II. And so he brought this data back and he gave it to a lady by the name of Maria Thorpe. And Maria Thorpe, this is a great story. Maria Thorpe was a cartographer. So he gave these maps to Marie, and she put this data together, and truly, she was the first person to understand and map the mid-ocean ridge. So she was the very first person to identify that there was a mountain chain on the bottom of the sea floor. Henry Hess gets all the credit. Marie is the one who actually did the work, the legwork behind it. For me, Marie is really interesting because she was a University of Michigan graduate. So that's where she did a lot of her studies, and she grew up just outside Detroit, just like I did. And she's still alive. So I got to meet her at one of the geology conferences, and so it was like a big deal for me because she's like a rock star and finally like a founding mother of geology. So in 1965, Henry Hess publishes a paper explaining this discovery. So this is the first time in scientific literature that this was written about. And what he suggests is that there is a mountain chain that's on the bottom of the seafloor. He calls it the mid-ocean ridge. And moreover, because he's a geophysicist, he suggests a mechanism as to how the mid-ocean ridge was created. And so he's suggesting that there are bodies of magma that upwell, and they upwell at what's called the Rift Valley, so the center of that mid-ocean ridge. And he suggests that those magma plumes are density-driven systems. So as that magma comes up to the surface, they have convection cells within them. So you have magma that's hot, it rises to the surface, it cools and condenses. And so that motion within the magma is what's acting as a driver for the motion of the seafloor spreading. So you know that those are called divergent plate boundaries. So Henry Hess is discovering the mid-ocean ridge, which will later be called a divergent plate boundary once the theory of plate tectonics is established. So this is like the very first step in identifying how these plates are actually moving. Next, what he's suggesting is that not only is there a mid-ocean ridge, but the edges of where those mid-ocean ridges end must be a subduction zone. So you have opening, and then you must have subduction, because the Earth, remember, is staying one constant size. So you have to have opening and you have to have subduction. And so he's putting these ideas together and presenting them in this paper in 1965. He confirms the mid-ocean ridge is an area of high heat, and he does that by some funding that he receives from the National Science Foundation to go back and take a look. So he's using essentially like heat radar to measure and monitor where the mid-ocean ridge is. So it's going to be hotter at the center of that ridge where the magma is allowed to come up closer and closer to the surface. Now, the next part of the equation is moving towards this idea of paleomagnetism. So there was another group that was out of Harvard, and they're called Vine and Matthews. And Vine and Matthews are on the heels of Henry Hess, and they published a paper in 1968. So Henry Hess, 1965, Vine and Matthews, 1968, out of Harvard. Okay, so Vine and Matthews are also geophysicists. And after we moved out of the war, what had happened is that the oil industry allowed the release of cores. So when you drill a core at the bottom of the ocean, and you do that for oil and gas exploration. So the oil and gas companies released these cores to scientists who wanted to look further and study the bottom of the seafloor. And so Vine and Matthews were one of those groups. They're geophysicists, and they were interested in magnetism. So you'll remember looking in laboratory at a mineral called magnetite, and magnetite has magnetism. So how that magnetite is formed is that you have rocks that are originally deposited horizontally on the surface. You have magnetic minerals that float down to the bottom of those sea floors, and eventually those get trapped in the form of sedimentary or types of rocks and or minerals. So Vine and Matthews are looking at these cores, and they give it to a graduate student, and they say, graduate student, figure out the magnetism of these rocks. And so they go and they do. And what the graduate student does is he comes back and he says, I'm looking at this core from oldest to youngest, but what I notice when I look at the magnetism is that the southern part of the magnet is at the top of the globe, and the northern part of the magnet is at the bottom of the globe. And that doesn't make any sense, right? So when you orientate ourselves on the Earth's surface, north is up and the southern hemisphere is south. And the graduate student found an opposite signature in this core. And so Vine and Matthews are like, graduate student, you're doing a terrible job. Go back and do it again. And they come back with the same data set. And so Vine and Matthews are like, gosh, if you want something done, you got to do it yourself. And they go to the lab and do it, and they find it. So what's interesting is that they discover that every 500 million years, the Earth goes through a reversal of magnetism. What? That's a big concept. Every 500 million years, the Earth goes through a magnetic reversal. So what we know today as north is up and south is at the bottom is flipped. So this is a huge concept in 1968 to be published about. Now, how this relates to the story of plate tectonics is that Vine and Matthews went back to those cores on the ocean floor because they were looking for a pattern. And what they were able to establish is that those magnetic reversals have been incorporated into the ocean floor. And what they noticed is that at the Rift Valley, you get also a younger signature of rock, because remember, they're able to age date these rocks too. So they go back and they age date the rocks, and they notice that the younger portion of that Rift Valley is closest to the mid-ocean ridge, and then they get consecutively older away. And that's what this diagram here is showing you. So you see 1 million years. So it's like a conveyor belt, 1 million, 2 million, 3 million, 4 million. So as you move away from that Rift Valley, the rocks get consecutively older. So essentially, Vine and Matthews is confirming everything that Henry Hess has published in 1965, when he's starting to talk about seafloor spreading. He's saying that a body of magma is moving up to the surface that has convection cells, and that makes sense that the rocks at that Rift Valley are youngest, because that's the point where the magma is coming closest to the surface. So these papers combined are helping to establish the idea of plate tectonics. When Vine and Matthews looked at the age dates of the rocks on the seafloor, they find that at the very edge of those divergent plate boundaries, and a divergent plate boundary ends at a subduction zone, they find that the maximum age of the rocks on the bottom of the seafloor are only 200 million years old. So think about that. Everything up to this point, we said the age of the Earth is 4.6 billion years old, right? So we age dated those rocks up in the Upper Peninsula in Australia, in the interior, and on Greenland. They date to 4.6 billion years old. So that's where we establish the age of the Earth based on uranium disequilibrium series dating. Here in 1968, Vine Matthews coming up, like we've looked at the rocks on the bottom of the seafloor. We understand that at the Rift Valley, those are 0 years, but the maximum age is only 200 million years old. And that's because as that divergent plate boundary is being created, it's also being subducted on its edges. So remember, the Earth is growing at those divergent plate boundaries, but they're being chewed up essentially at those convergent plate boundaries. So when we look at the ages of the seafloor on this map, we can see the younger colors are in the warm colors, and the older colors going to the middle or late Jurassic are in blue. And so you can see that there's very little blue color on the map. So the younger rocks are in the red color. They represent some of these geologic epochs, Miocene, Oligocene, Eocene. And then by the time we get to the edges of those Jurassic, they're being completely chewed up. So it is these ideas of divergent and convergent plate boundaries that allow us to come up with an idea and confirm what Alfred Wegner was trying to present in 1910, that the plates, in fact, are moving. This was established by the Wilson cycle. This was also published in 1968. That's an error on the screen. So the Wilson cycle was published in 1968 after Vine and Matthews. And so the Wilson cycle is plate tectonic. So it pulls all those ideas together. So it says a basin, you're starting at a craton, right? So you're starting at a craton is another word for continental crust. And you have a body of magma that's subsurface. That body of magma, called a hotspot or magma plume, builds up intensity. What you remember from that last lecture is that will create a divergent plate boundary or a triple point junction. And then once you start to have the spreading of a divergent plate boundary, that divergent plate boundary must end at a convergent plate boundary or subduction zone. And so you're opening and closing that basin. And as you're opening and closing that basin, you're creating a supercontinent. So you're pushing all that land mass together. And so what is interesting is that Pangea cycles happen every 500 million years. So you have, so you push those continents together every 500 million years, you pause, and then eventually they break apart and they push together on the other side of the globe. And so you get this cycle that happens every 500 million years. So if we say the Earth is 4.6 billion years old, that means that there have been 9.5 Pangea cycles that have happened over geologic time. Wow. Is your mind blown? Yeah, mine too. There have been 9.5 Pangea cycles that have happened over the course of the planet. And so remember, again, very first day of class, we talked about the Precambrian record. And we said the Precambrian is from 4.6 billion years to 570 million years. And it represents 80% of all geologic time, but very little of that record is left. It's either not left because of plate tectonics, been destroyed, or it's been buried. So it's really hard to get to. So that's because of these opening and closings of the Pangea cycle. So hopefully now this makes a little bit more sense when we look at plate tectonics here in this map. And so we can have an understanding of where your convergent plate boundaries are and where your divergent plate boundaries are, and the overall direction of movement. So one thing I want you to ponder a little bit is the question, which of the oceans are being closed? So are we at modern day, are we closing in on the Pacific Ocean based on this plate tectonic map, or are we closing in on the Atlantic Ocean? I'm going to pause here, and I'm not going to tell you the answer because I really want you to think about that. And we'll talk about that a little bit more in class. So after the Wilson cycle was published in 1968, it became a theory. And the reason why it became a theory is because in the world of geology, this kind of tied in so many different concepts that everybody became in agreement. So when we were curious as to why mountains were on the edge of continents, well, those are on convergent plate boundaries. So when you have a convergent plate boundary, you have mountain uplift that results. So here, when we look at this map, well, that makes sense. What's highlighted in orange, those are all convergent plate boundaries. That's called the Pacific Ring of Fire. The Pacific Ring of Fire is a convergent plate boundary. So it locates where our mountain chains are on the edge of continents. It also helps us to understand earthquakes. So if we were to look at the location of earthquakes, like we do on this world map, your biggest and baddest earthquakes are going to be along the Pacific Ring of Fire or at convergent plate boundaries. That helps to tell us something about the origins of tsunami events. So the location of where you anticipate a tsunami event. So I hope you understand that this idea in 1968 was revolutionary. And yet again, what had to happen was we had to overcome a technological boundary. So we had to have the mapping of the sea floor in order to understand that the Earth is organized into plates and that those plates have some type of motion. So fascinating stuff. I'm going to end here for today. You've been a wonderful audience, and look forward to that quiz that's coming up.